The Nile. For millennia, it has been a source of life, culture, and commerce for Northeast Africa. Without the Nile, there would be no Egypt. And without the water from the Nile, there would be no pyramids. Stone by stone, the Egyptian pyramids were constructed by harnessing the power of water rather than ropes, ramps, and the strength of men. The Egyptian pyramids were built at a higher elevation, on an open plain, to be visible without obstruction to Re, the god of the sun. Scholars say that beside each pyramid was a mortuary temple connected to a causeway. At the other end of the causeway was a valley temple. Many envision an arid landscape surrounding the pyramids, as it is today. This theory hypothesizes that it was just the opposite. Let's think about the pyramids differently for a moment. This theory presumes that there was a lake or water basin with a harbor beside every pyramid built in ancient Egypt, and that each pyramid was connected to this harbor by a causeway. The causeway ran from the pyramid down to a temple, frequently called the Valley Temple, located at the nearby lake or water basin's edge. This theory suggests changing the name Valley Temple to the more appropriate Harbor Temple, due to its proximity to the water's edge. Saqqara, an expansive Egyptian burial ground where some of the 5th and 6th dynasty pharaohs built their pyramids, is home to Unis's Causeway, one of the best preserved examples of the causeway. There are locations in this area with multiple pyramids that are built near one another with causeways leading towards a body of water. The causeways led to the lake, and this lake was connected to the Nile River by man-made canals. Ancient texts confirm that pharaohs called upon the Egyptian people to build such canals. 4,400 years later, this lake has dried up. However, evidence remains that lakes were present during this time. When Pharaoh Khufu sent his builders to survey the future site for his pyramid, they found that the Giza Plateau offered everything needed for a colossal pyramid site. The Giza Plateau was near the Nile River and a probable small lake. The area was made of limestone layers and offered a solid foundation to support the massive pyramid. The limestone also supplied core stones for the pyramid. Fast forward to the 1980s, an American-British consortium, Ambrick, drilled 72 boreholes before installing a new sewage system east of the Giza Plateau. These boreholes yielded information about the terrain, precisely sediment deposit depth below the surface and elevation to sea level. This data and research from books, maps, photographs, and other materials was used to develop this revolutionary theory of how the Egyptians used waterways to move building material within the Khufu Basin. Most scholars agree that over time, the Nile River has migrated eastward. The former Nile Channel, or Western Branch River, is now referred to as the Labini Canal. The Labini Canal is next to the Giza Plateau. Archaeologist Dr. Mark Leonard showed that there is silt and clay 2 to 5 meters above sea level in the Labini Canal, confirming the old Nile River's location and depth. The Nile River was the only possible source for this silt and clay. At the foot of the Giza Plateau, there was likely a small permanent lake. The boreholes showed sand, silt, and clay bordering the Wall of Crow on the south and Khafre Harbor Temple on the west. The deepest, lowest point of the basin was the same depth as the lowest level of the ancient Nile River, or branch channel, as it is in front of present-day Khafre Harbor Temple. The probable small lake Khufu's builders found when scouting the pyramid location would have been in this area. During the spring and early summer, the Nile Channel water level was approximately 3 meters deep, which was 5 meters below the floodplain. The water table in the Khufu Basin would have also been lower, 0 to 3 meters deep. At this time of year, water would only be present in the probable small lake. There would be enough water to operate canals to the pyramid base and sluices on the pyramid all year. Still, without a method of controlling the water flow, water transportation would have to stop within the basin for a few months due to low levels. Employing their knowledge of agricultural basins, the Egyptians would have constructed a dam in the Khufu Basin to make it possible for water transport to continue all year. When the annual inundation began, the Egyptians allowed the Nile water to flow into the basin, traveling between two mounds, Nazalet el-Sisi and Nazalet el-Batran, bringing an influx of water to the Giza Plateau. Khufu's builders dug, expanding the existing canal between Nazalet el-Sisi and Nazalet el-Batran, making it broader and deeper and connecting the Nile with the probable small lake. The canal expansion made it possible for the Egyptians to deliver stones and supplies even closer to the Great Pyramid base. During this time, large boats were delivering massive granite for the interior pyramid chambers from Aswan and casing limestone for the surface of the pyramid from Tura. The Egyptians were unloading the cargo close to the Khufu pyramid from the Khufu quarry side. This proposed site was near the current Khafre Harbor Temple location. In anticipation of dam construction, the Egyptians prepared stones and clay at the top of the bank where the dam was to be built. At the moment the water began to recede, construction of the dam in the Khufu Basin started. Dams were not a novel concept to the Egyptians. We know they had experience constructing the dam at Sa'd el-Khafara. It is common knowledge that beavers are masterful dam builders, and that the Russians did a good job building the dam at Aswan. If these engineers could master the art, it is safe to assume that the Egyptian engineers who built the Great Pyramid were more than capable of building a dam in the Khufu Basin, which could have been built using short vertical limestone walls on both sides of the canal bank, beginning at the canal bank's lowest point and extending to its highest point. The dam's base could be one layer of stones on the bottom with a wooden railing that had ropes attached. The ropes acted as a guidance system for the stone placement during the dam's construction. By the end of flooding, when water began receding, the dam would be completed by sliding the ropes from the canal banks into the canal's center and dropping stones into the water where needed. Clay, widely available tafla, would have sealed the dam from leaking. Water levels were constantly changing due to leakage, evaporation, and use by sluices. As a result, the water level in the basin would slowly recede, and the top part of the dam, above the water level, would be disassembled. Stones above the water level would need to be removed and placed on the canal bank to be reserved for use during dam construction the following year. The water level recession was also why the main harbor and Khufu Harbor Temple had lower water ramps. On both sides of the dam, workers built sluice lines to allow transport during periods of reduced water depth. The lowest sluice was at the same depth as the lowest water level in the Nile in the early summer. The sluices line escalated in height to the top of the canal bank and back down to the lowest level on the other side. When the dam was closed, boats from the Nile would have delivered materials to the dam, where they were reloaded onto barges. Barges carrying smaller stones and goods needed for construction and worker support were lifted in the dam's sluices to enter the basin. To move materials from the basin to the pyramid, Egyptians would have either dug a canal or built a canal on top of the limestone running beside the Khufu quarry. Inspector Merer described a delivery point in an ancient papyrus found at Wadi el-Jarf, which this theory proposes is the area close to the present-day Khafre Harbor Temple. The Egyptians stored materials at this site, including granite from Aswan and casing limestone from Tura, before moving it to the pyramid base. This theory suggests a canal ran from the Khufu Basin to the base of the pyramid. The canal started close to the Khafre Harbor Temple's present site, traveling west and slightly north for about 350 meters to the Khufu quarry. At Khufu quarry, the canal turned north, stretching approximately 200 meters before reaching the canal surrounding the pyramid base. The Egyptians would have dug this canal in the sand or built the canal on top of limestone terrain. To prevent water leakage from the canal, the Egyptians could have used bentonite clay and lime mortar, typical of all stone-to-stone joints between canal stones and surrounding stones. Short pieces of floating papyrus reeds placed on the water's surface could offer shade and slow down evaporation. Every aspect of the Great Pyramid's construction required the use of water. Constant water use led to fluctuating water levels in the Khufu Basin. Water flows from a higher sluice to the sluice below, making transportation between different elevations possible. The Egyptians used barges to transport stones and materials through sluices for pyramid construction. The barges were lifted by increasing water levels. The average weight of the core stones used to build the Great Pyramid was 2.5 tons, and the largest stones were 60 tons. A larger barge and more water would be necessary to lift the heavier stones from one sluice to the next. The same principle is used in the Panama Canal, where the largest cruise ship, the Norwegian Bliss, weighing 168,028 tons, passed through 6 sluices on May 14, 2018. The Norwegian Bliss was 2,800 times heavier than the largest stone used in pyramid construction. Each sluice requires 2 workers. One worker operates the lever that opens and closes the sluice gate. The gate is raised by hooking the short arm of a lever to the top of the gate, providing enough force to raise the gate with 2.74 meters of water pressure. 2 workers are required to move the barge from one sluice to the next. The levers work on the same principle as a shaduf. The average weight of the stone being transported was 2,500 kilograms. The full cycle of the sluice takes 4 minutes. Raising a stone 2 layers higher on the pyramid, 1.37 meters, would require 6,370 liters of water. 2 workers on either side of the canal would push stone A from the canal into sluice 1. The gates of sluice 1 and 3 would be open or raised. The water level in sluice 1 and the canal would be the same. As stone A is pushed into sluice 1, stone B is pushed into sluice 3. The gates in sluice 1 and 3 would then lower or close. The gates for sluice 2 and 4 would raise or open. Water from sluice 2 would drain to sluice 1, and simultaneously, water from sluice 4 would drain into sluice 3. Stone A would lift into sluice 2, and stone B would lift into sluice 4. The gates for sluice 2 and 4 would then lower or close, and the gates for sluice 1 and 3 would raise or open. Water from sluice 1 would drain into the canal, and the water from sluice 3 would drain to sluice 2, raising stone A. Simultaneously, the water from the highest sluice would drain into sluice 4, raising stone B. Shadufs were used to lift water to the highest sluice level. Water from the higher sluice will drain to the lower sluice and raise the barge carrying the stone. The same amount of water is required to raise as many stones as there are sluice levels. If there are 50 sluice levels, the same amount of water will raise 50 stones.
Upper sluice, lower sluice, and the lowest one. Gate between the lower sluice and the lowest sluice is open, and the water level between those two is the same. Barge is slowly floating from the lowest sluice into lower sluice. I am going to close this gate between the lowest sluice and the lower sluice. It is very easy to close this gate because the weight of the gate pulls down the gate. The gate for the lower sluice is closed. Now I am ready to go and open the gate for the upper sluice. The water pressure is tremendous. Water from upper sluice drains into lower sluice. I am gate for the upper sluice. A little more and more. You are seeing barge go up. You are witnessing how fast and easy water is lifting this stone. So please do not underestimate the power of water. This is 48% of 2.5 tons stone used to build Great Pyramid. Now I am ready to push barge with stone into upper sluice, and a cycle of lifting will be repeated over and over again. This is how the stones were transported from the base of the pyramid all the way to the top. Thank you.
A shaduf is a long pole balanced on a crossbeam, with one arm of the pole extending farther from the crossbeam than the other. A bucket and rope are attached to the long arm, and a counterweight is attached to the short arm. The counterweight is used to offset the weight of water being lifted by the bucket.
I do have the 5-gallon bucket of water. Could you please zoom it in? This is full bucket of water. It is 5 gallon. Each gallon is 8.34 pounds, which gives us 41.7 pounds. This bucket of water, which is 19 liters and approximately 19 kilos in 17 degrees centigrade. And if I am using this shadow, if this shadow is properly balanced, I can lift this bucket of water 41.7 pounds easily with one hand, which I am going to show it. Easily. One hand, up and down, up and down. And also, which is very important, I can hook it and bring this rope back with one hand. Up and down. This is how water was transported from the bottom of the pyramid all the way to the top, to the construction site where was needed. One bucket of water was transported from the bottom, was never emptied, just changed Shadufs and went all the way to the top. Thank you.
When a shaduf is appropriately balanced, a worker can lift a 19-liter or 5-gallon water bucket using one arm. Every fifth layer of the pyramid had a shaduf installed, with one worker operating each shaduf. The second worker was needed to unhook the full bucket of water from the lower shaduf and hook that bucket to the higher shaduf. These shadufs transported full buckets of water from the pyramid's base to the highest sluice, moving each bucket of water from one shaduf to the next. The water elevation in the Khufu Basin was 13 meters above sea level. The elevation of the Khufu Quarry was 40 to 45 meters above sea level, and the elevation of the pyramid base was 60 meters above sea level. The base of the pyramid was 47 meters higher than the water table in the Khufu Basin. Sluices were used to manage the elevation change. The Great Pyramid could have been built in 2 years, requiring a constant flow of stones to the pyramid base. 3.5 stones per minute would need to move through the supply and delivery canal, and 3.5 stones per minute lifted onto the pyramid. It took 4 minutes to lift one stone in each sluice, meaning a header system of sluices was necessary to deliver the frequency of stones required to enable construction. Every header system between Khufu Quarry and the pyramid base had 15 sluices, each with one sluice in the center for the greatest stones and 14 additional sluices for average-sized stones. The canal from Khufu Quarry would have supplied a constant flow of stones and plenty of water necessary to construct the pyramid. The pyramid's base was precisely leveled with water, and every layer was verified by the same method. Many scholars question why the subterranean chamber was never completed. This theory suggests workers began construction on the subterranean chamber after the Great Pyramid was finished. If the chamber had been present, the constant water used during construction would have flooded the area consistently. While workers were digging the subterranean chamber, Pharaoh Khufu died. Khufu's son, Shadufs, started working on his pyramid at Abu Rash immediately after becoming pharaoh, halting the construction on the subterranean chamber. Egyptians built a canal on top of the limestone surrounding the base of the pyramid, which supplied stones and water for construction. Egyptian engineers calculated how far the canal needed to be from the pyramid's base to accommodate the length of sluice lines that would reach graduating layers of the pyramid as construction progressed. In the first year of construction, the Egyptians needed 20 sluice lines extending to the pyramid's 40th layer, 2 for large stones and 18 for average stones. 14 of the 18 lines used for average stones were continuously operational, and 4 of them were interchangeably rebuilt to reach higher layers of the pyramid. During the second year of construction, the number of working sluice lines reduced from 14 to 12 to 10, and by the 120th layer, only 6 were operational. Above the 120th layer, 4 sluice lines were used, and then only 2. 2 sluice lines reached the top of the pyramid. There were water canals on the lower layers of the pyramid, up to the 120th layer, making it easier and faster to transport stones to the necessary locations. Due to limited space on layers above the 120th layer, the Egyptians rolled or slid stones from the sluices to the necessary location. "20 water-powered sluice lines made it possible to raise 1,839,600 stones in the first year, and 788,400 stones during the second year of construction, totaling 2,618,000 stones. The Great Pyramid is made of approximately 2,500,000. During the first year of construction, 11,904 workers operated Shaduf lines, and 1,680 workers operated sluice lines, totaling 13,584 workers. During the second year of construction, 22,260 workers operated Shaduf lines, and 3,168 workers operated sluice lines, totaling 25,428 workers. Building the Great Pyramid in 2 years is feasible, but due to the seasonal availability of workers, weather, and other variables, constructing the pyramid likely took more than 2 years. The Nile, which provided an abundance of life and vitality to Egypt, was instrumental to the construction of the pyramids. This surviving wonder of the ancient world owes its creation to the waters of the Nile, painstakingly moved by sluice, stone by stone, giving us a marvel of human ingenuity that has stood for millennia. I would like to thank architect Thomas Enstrand, AIA, licensed in the US with 40 years of experience, for technical assistance. I would also like to thank Megan Peake-Moore for assistance with the creation of this video, starting from an idea, through the script, and to the final product.